All right, one cycle may be also referred to as a wavelength. Amplitude. Amplitude is the peak value. So we have peak, as I showed you in the drawing up here. I'm going to go back. We had peak right here, and we had peak to peak. So you have to make sure that you are keeping things consistent. So let's see, peak to peak, peak to peak, which I could abbreviate like that if we get into something like peak to peak, is the peak value, U value times 2. Or I could say peak is peak to peak divided by 2, right? It's 1/2 of that. And let me see. So if I have 120 volts peak to peak, wait a minute. Yeah, if I have 120 volts, we'll do it this way, is peak. What is peak to peak volts? Did you say 140? Are you using your calculator again? What is my peak to peak voltage? 240. 240 volts. It said 140. Whoa.
Record this. It's re-recorded. It's
All right, and always, especially when working with aircraft, because you have so many different voltages, the component and frequencies. The component being installed must be rated for the frequency used. Who are my world travelers that have different frequencies in other countries?
In Russia, we have 50.
In Russia, what is the frequency?
50 gigahertz.
50.
Yeah.
So what happens if you try and use stuff made here in Russia? Does it still work?
It doesn't work because you need to, it will be burned because it's 240 volts in one line.
Oh, yeah, 240 volts in one line. All right, so 240, 50 hertz.
Yeah.
And here we are, what do we hear?
120.
120 at 60 hertz. Okay. All right, so now that we got that, can I move this or I need to keep it here? All right.
Kevin,
Yeah.
I'm kind of confused about like alternating current versus DC. So I know DC, like it completes the whole path. So for alternating current, I know like switches from positive to negative. Does the electricity still complete like a full path?
Still the exact same thing. Nothing has changed.
Okay.
But it's weird to think about. It goes around, then it turns around and goes the other way. Then it goes the other way, the other way. It's doing it like speed of light. So it's going back and forth, back and forth. So if you think about a power line that's running from here, and let's say it's got to go all the way to wherever it's produced. I don't know where it's produced at around here. Anybody know? It used to be out at Rancho Seco. It would make that trip. It would actually go that way, this way, that way, this way, that way, this way. It's making the whole trip back and forth. Well, so it's actually doing that, which is kind of a weird thing to think about. Yeah.
The higher the hertz rate,
Yeah.
the more efficient.
Uh-huh. Okay, so I want to talk about phase. This is where it can start to be a little confusing, but we really have to understand phase for what we're going. Can I move this?
Oh, you're good to go.
Am I good to go?
Make sure Justin's cool.
I looked at him and he gave me the nod. He gave me the nod. So phase. Phase. Phase is the angular difference between 2 points on an AC waveform, right? Everybody understands that. Is
Totally agree.
the angular difference between 2 points on an AC waveform. And let me see. So if I'm looking to get an oscilloscope, we'll do some colors. And I have 0 right here. Oops, 0. And I said this is my voltage, right? So I said my voltage goes up and down and up and down. And I said this right here is blue. This is 0 degrees. This is 90. This is 180. 270. 360. 360. Everybody remember that? All right. So here, 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 and here. All right. Now I said this is voltage. Green is voltage. But we got to think about amperages out there too, right? So if we plotted amperage, what do you think amperage is going to do? Is it just going to go straight line like DC? Okay, it's the same waveform. It's a little bit harder to draw. Now, in your experience, is voltage the same as amperage, or is voltage usually higher than amperage? Okay. What's higher? Voltage. Okay, so I'll let my amperage be lower. So it's going to kind of do the same thing. Right? And if it does the same thing, and it matches the zeros, and it matches the peak, and it matches down here, that is in phase. Right? So the angular difference between anything is the same. Where's my peak amperage?
Right there.
90 degrees. Where's my zero amperage? 180. Where's my negative peak? 270. And my back to 0. So that's in phase. Right? But we can actually get into a situation, and that's what we're going to talk a lot about, where it's out of phase. So it's kind of hard, but it would. So if it went like this, where's my 0? Is at 90. My peak is at, it's supposed to be. Well, I tried to draw 0 right there, but 0 at 270. So you can see how everything is now out of phase. It's out of phase by how much? 90 degrees. Because if a 0 is here and the 0 is here, and the difference is that, this is out of phase by 90 degrees. And this can actually happen, where the amperage and the voltage are out of phase. They're happening the peaks are happening at different times. The zeros are different times. This is not an efficient way to operate anything. It's inefficient, and you're going to have power losses. So here you have a generator that's working just as hard as always, but now things are out of phase, and so your components don't work as well. It becomes out of phase, and so it becomes inefficient.
Where's the power going? Like in DC, it would be going to heat or something. What is it going through when it gets out of phase?
I haven't thought about it.
Okay.
I think maybe as we get into it, we'll kind of be self-explanatory. You'll see what components are doing and go, that's where it goes. Yeah?
Yeah, how do you differentiate the lines on the oscilloscope if you have current and voltage? Can you see both?
I've never actually set it up, but yeah, I think you can, where you can set it up and see them. But we're going to mathematically figure it out. It's not that hard.
Yeah, but if you see two lines, which one is which?
Oh, you would know, because you have 2 channels on your oscilloscope. So it'd be channel B.
Oh, okay.
And you can turn one off, ground one, turn one on. You could move one and not the other, and so you'd be able to see it.
They naturally want to get out of phase.
Do they naturally want to get out of phase? I don't want to say they naturally want to. I think they never really asked them, but if I did ask them and said, we sat down and had an honest hard talk, they'd say, no, we want to be in phase, but you people are always putting inductors in things, and we can't help it. So that's what they would say.
So there's no point in getting something out of phase, or
Oh, it's bad. You don't want it out of phase. But we are naturally, because of the components that we use, are going to be throwing it out of phase. So just where we're going is inductors is one of our most useful things. It's a coil of wire. We use coil of wire in everything. And so inductors cause it to go one way, capacitors cause it to go the other. We tend to use a lot more inductors because of motors, just think about what SMUD's dealing with. It's hot. Everybody's running their air conditioner. What does an air conditioner have in it? It's a motor. Motors have, you got a fan, you got a compressor, you get, the only capacitors I think is a start capacitor that, but that's gone once the thing starts. So air conditioners are all motors. So motors are going to throw it out of phase. So over at SMUD, they've got banks and banks of capacitors to bring it back the other way. So capacitors go one way and motors go the other. All right, so that's phase. What else do I have here? Okay, so we have that. I kind of went off notes here. There's a thing called polyphase. I mentioned that. So what did I say polyphase was?
Just multi-phase.
Okay, so some AC circuits use multiple phases. Like three-phase. Three-phase is pretty common, especially if you're running machinery. I think we have some three-phase stuff around here too. It's actually quite common, but you have to have special lines running for that.
Look at your new Magnaflow.
That's single phase.
Is it really?
Uh-huh. So three-phase. It's a very low duty cycle, and most of the stuff just running 110 on it is 120 degrees apart. I could try and draw it, but it's very difficult, and I'll probably screw it up. But you have phase 1. I already screwed up. And then you have phase 2 is 120 out, so that's 90. So it starts its phase. Then you have phase 3, which is another 120 out. It's doing its phase.
They did pretty good.
And what you get is, instead of having a peak here and a peak here, you have a peak, a peak, a peak, and they're supposed to be spaced equally apart. And so all the peaks are actually quite closer to apart. So you're running it at different phases, so you constantly get these peaks, which gives more power to the circuit, which means you can run a smaller motor. So, and like I said, in machine shops and stuff like that are normally using large motors, that can decrease the size of the motor. All right, so explain the volts amp phase, so I'll come back around to that. So let me see, I think I should be on, what, C? Hey, look, I am. It's holding together. VOL, volts / amp. Amperage phase. All right, so in an AC circuit, it is possible for the peak voltage to happen at a different time than peak amperage. I'll write that for you. In an AC circuit, it is possible for the peak voltage to happen at a different time than peak, at a different time than peak, possible for the peak voltage to happen at a different time than the peak amperage. This is an out of phase circuit. And there's a little trick for remembering what happens. It is called, so remember this, remember Eli, the Iceman. Eli the Iceman tells us everything we need to know. Well, who is Eli? Well, he's an Iceman. That's all you need to know about him. So, let's talk about Eli. E-L-I. Inductance. Inductance, which is coils and such, is represented by L. And what does E represent? What?
Voltage.
Voltage? That's new. What is I?
Current.
Current. All right, so if you have a circuit with an L, and we're going to get to Iceman, what is the C going to be? Capacitance. C is capacitance. So right now we have Eli, which is represented by inductive. So if you have an inductive circuit, which means it's mostly influenced by inductors, which are what?
Motors.
Coils and motors. We'll say coils. Inductance is represented by L. So in an inductive circuit, E leads I, because E comes first. So E leads I. So so current is going to lag behind, voltage is going to lead it. Ice. That's capacitance. Is represented by C. So in a capacitive circuit, and a capacitive circuit is a circuit that has more capacitive reactance than the inductors. So you can have a lot of inductive reactance, you can have a lot of capacitive reactance, and if they're equal, then what?
It's in phase.
It's in phase. But if the capacitance gets a little too heavy, we have more capacitive reactance, then what's going to happen?
Out of phase.
It's going to be out of phase, and what leads?
Current.
The current is going to lead the voltage. If I have more inductors,
Voltage is going to lead.
voltage is going to lead. So, you know, over at SMUD, my father-in-law worked there. He said they had big rooms with large capacitors, and so all these motors would start coming on. People are using their motor, hair dryers and their curling irons and whatnot, and air conditioners. What's going to happen? Is that an Eli or ice condition? Eli. So the voltage is going to lead, and so the current's going to start lagging behind. So what they do, they go in, they just put on some capacitors, add these capacitors, and the capacitors would go the opposite, start bringing it back in phase.
When you say that the current leads the voltage, so you're having more current than voltage?
Not more current than voltage.
It's ahead of it.
It goes back to this drawing here, where the black represents, well, the red is where it should be, but then it moves towards black. They actually don't happen at the same time.
No, I understand that.
Oh.
But the way that I was kind of thinking about it when you said that was that there's more current.
Not more
That
current.
mission, okay.
Nope. So you have more voltage, you have lower current, but they should happen at the same time. They should follow the same curve. They should hit zero at the same time, hit peak at the same time. Then it's something that is in phase. You get out of phase, and the zero happens here when so the green is our voltage. So here's zero, but then zero moves over to here. You're out of phase. Prince had.
If you were to move the phase to the next waveform,
Move it all the way over to the next waveform.
would it be effective, or would it be 180 or 360 degrees off? Or yeah.
Oh, you'd have to go all the way that you wouldn't know.
No, but if you were to add enough in
Yeah, you just keep moving it all the way over till it gets all the way back in phase. It's phase is phase.
so why would you use capacitor?
I wasn't there for that committee.
Okay.
So why not just add a whole shitload more inductors until it's all the way out of phase? Because then you have to go all the way through. And what do you think's going to happen? I don't know the answer to this. What do you think's going to happen to our stuff when things get 180 out of phase? So see, the thing that makes most sense to me, if you get 2 degrees out of phase, put enough capacitors in to bring it back in.
Well, I guess what I'm saying is it comes back around. So you can.
But you're saying, well, we got 2 degrees out of phase. Let's throw on the other
Well, not like that.
358 degrees over here.
Gotta get it back in.
That would work. It's just it's really hell going through that phase where one's going up and one's going down. I don't
There would be
know.
no downside to bring it over a whole waveform.
Well, I think it'd be a huge downside when they're 180 out of phase and one's going up and one's going down and all the way through that.
180, 360.
Yeah, 360.
You can go through
No,
whatever you need to.
I know well, we're just getting off the subject on something I don't know. It doesn't matter. They don't do it that way. I'm pretty confident of that. Yes.
Yeah. Is that the way that you can tell if in a circuit that you have a bad capacitor if it's starting getting out of phase?
Yeah, add capacitor. Too much capacitance, add a coil. So, all right. So we're going to figure out how to figure this out, though. Let me see. I'll write this just so we know it. And you say, well, you didn't put it in your notes. A circuit. Yeah.
You didn't finish in a capacitive circuit.
In a what do you think I'm right? Help me out. In a capacitive circuit, what happens? I leads E. There we go. And you can look at it both ways. So if I look at Eli, I say voltage leads the current. I could also say current lags the voltage, right? It's the same thing. It's just that the voltage is ahead. So if Tim and I are running a race, well, Tim's going to beat me. So Tim's in front. We'd say Tim is beating Kevin, or we could say Kevin is behind Tim. So it's the same thing.
And
I don't know if I beat you. Tell me there's a plane to catch, and then I'll beat
Yeah.
you. But
A circuit that is out of phase. Out of phase is less efficient. And what gets out of phase? The voltage and the amperage. What about the resistance? Does it get out of phase? Okay, I'm glad some people are laughing. What is a stupid question? Of course not. Voltage is just resistance, right? All right. So that brings us to effective power. EFFECTIV. Power, effective power. All right. So I don't know. To me, this was kind of interesting when they come up with this stuff. So when you're measuring DC, when measuring DC, the effective power is the same. It's just what you get, right? So we did Ohm's law, and then we did pi, and pi was always just I times E. There's power, right? So we got the power. So in DC, the effective power is the same as the measured values. And it was not a problem. In AC, it's quite different. First of all, in AC, so in DC, the reason why it's a straight line. So pick any point in time, and it's going to be, well, what's the power? It's right there. It never changes. But in AC, it's constantly changing. So if we actually looked at a waveform, and we took a look at one waveform, and we picked all these little spots all the way around it, and we averaged all of those spots that I picked, what would be the voltage of the average?
0.
It would be 0. So is my voltage 0? Is that the effective value?
No.
No? All right, good thing, because that wouldn't work. So in AC, let me see, the maximum measured value only happens twice per cycle. The max, let's abbreviate max value, VALUE value, only happens twice per cycle. Therefore, how are we going to figure out an average? Because we just figured out the average would be 0.
Why would you need that? Why would you-
Because I want it. To figure out the effective value.
you couldn't-
So what's the effective value? If it's negative and positive, the effective value is what, 0? I'm sure somebody had to think about this to begin with. Hey, that's great. It goes positive, then goes negative. What's the effective value? I don't know. Add them all up and come to total. Well, I added up all these points, divided by the number of points, and came out with the mean value is 0. Okay, well, that didn't work at all. So how are we going to figure out the effective value then? All right. And I could write that the two cancel each other out, but I think you got that. But they don't really cancel each other out, obviously, or we wouldn't have AC power. Every time we turn it on, we get 0. Why do you get 0? Well, because it's effective as 0. It goes negative, The light, puts out light, and then it sucks the light out of the room for the next cycle. So.
Hope that's a question on the test.
The effective value. Why do I keep missing my U there? V-A-L-U-E, value. Looks like valve now. V-A-L-U. The effective value of AC is that which produces the same heat value in DC. All right, so somebody sat down and figured out, well, hey, we should just compare it to heat value. So take a resistor or a plug-in heater and run the heater off a battery, or you plug in the wall, but you got to get the same heat value. And I think about that as I think about my wife and Katie, as the winter is now here upon us, according to them, and they're already sitting at home under blankets and heaters. They're very concerned about the fact that they get the same heat value, whichever it is they're doing. All right. So let me see. I'll go with that. Let's see. What is the formula for power? All right, so it's pi. So the formula for power is P equals I times E. And if you ever look at that little wheel, and I told you I don't need to worry about it, and so far you haven't, it's I squared times R, or E squared divided by R. I don't know why I went this route, but I'm just going to go with it. Therefore, the heat produced is proportional to the square of the current. I shouldn't even go there. So to figure out the, I'm going to skip to the point here. So to figure out the average AC power, we average all of the values. Then we square them. And why would we want to square them? Hey, there you go, because this is like -1, -2, -3. So, and this is 1. So if we take all the values and we square them, what happens if you square... Oops, not square root, I'm sorry. That's why I just said that. If I square them, what happens to all the values? They all become positive. So take all the values, I square them, they become positive. Then I add them together. Then I figure out the average. Do I have an average?
Yes.
No, not quite, because I squared them. So it's going to be way too much. So how do you unsquare it? It's a square root. So there you go. Root, mean, squared. So you get it? So you take these and you square them. Square root. Well, it's true, but that's, I'm glad somebody got it. So that's why we say RMS value. So I'll put that. To figure out the average AC, to figure out the average AC power, we average all the squared values, then unsquare. That's not a real thing, but which is the same as saying square root. If this is really going to be one of those questions.
I don't know.
Okay. Why did they do it this way? I don't know.
What is the difference between that and absolute value?
Just stick with I don't know.
Does it matter? I've got to stop and ask, does it matter?
You're goddamn right.
I don't even know. I don't know. I don't know. I'm not a mathematician. Have I mentioned this? What was my primary job in life?
Aircraft mechanic.
What was it what?
Aircraft
I want
mechanic.
to hear Prince say it.
Okay.
I did what for a living? Was not a mathematician. I was not an electrical engineer.
I think I know why.
No, I'm just.
I know. I wondered it myself too. But the difference between you and I is I didn't raise my hand and ask somebody because I didn't care. I'm just like, I don't really give a
Just
crap.
ask Tom tomorrow and laugh.
Yep, there we go. Tom listens to all of these. Tom, Prince wants to know why they didn't just do the absolute value. And you know what he means by that? Because if you take the absolute value of 1, it is just 1. And it should have worked, but it didn't. Actually, I think I do know the answer to that, to be honest with you. I wrote it here, but I crossed it out because I did. Sometimes I wonder myself, and I forget. And then I look at my notes, I'm like, yes, I did want to know this at one time. So now, this part that I won't write it because I said, no, this is actually different than just an average value. The average of 2, 4, 6, 8, and 10 is 6. You don't have to know this. The average of 2, 4, 6, 8, and 10 is 6, right? You add them all up, divide by 1, 2, 3, 4, 5, you're going to get 6. It's going to be close.
We're rolling with it.
Okay, the RMS. So if I square them all, then add it, then divide, that's root mean squared, is going to be 6.63. So squaring the number gives us, let me see.
That's my
Are you happy, Prince? You're the only one.
It comes out at a different number. It is actually more accurate.
Okay.
See, look, he makes me a better guy. Even though,
After you went on a rant?
do you know before I met Prince, I didn't drink alcohol?
Kevin, you're not fooling anybody. You got like 6 kids.
Or sniff glue.
That's right. Take another swig, Kevin.
I also wrote some. Let's see. The squaring the number gives us. Let me see. I don't know where I got this. 4, 16, 36, 64, 100. That ended up equal 220. The average is then 44. The square root of 44 is 6.63. So I prove it out with math that this is actually the true RMS value, and it's actually more accurate than that. So apparently, Prince and I think alike. I just forgot because I'm older and I don't remember stuff. So I have to think about it. I missed
What have you
it.
been drinking?
Is that no? Is that
That's what he said.
That's what he said. He said,
Oh.
"What have you been drinking?"
who said that? Oh, yeah, coming from him, that's pretty funny, actually. I just expect that from you guys. All right. Okay. And boy, I don't know if I'm gonna write this. Another way of saying this is all the instantaneous values of the sine waves are squared. The results are added together, divided by the number of results to get an average or a mean. The square root of this gives the effective voltage. This is called the root mean square value. This is called, back on track. This is called the root mean square value. Mean means average. Root is the square root. Squared is squared. So that's where they get that. They should have called it the squared root average mean or something. All right. That was somehow got to 4. So there you go. So 1, 2, and 3 were all of this stuff. All right, 4. Point number 5. All right. Since this is not practical, to actually add up all of the instantaneous values, because you need quite a few points to actually. Since this is not practical. We use the following formulas. Now, at this point, I highly suggest you take a piece of paper out and you put on the top formulas, because we are going to have so many formulas, and you are going to want to have them on, I think, one piece of paper where you can just pull them right out and you can look at it and say, that's what I need. Well, I would like to say yes. And in my perfect world, I would say whatever you have on your formula sheet be good, but you'd write all kinds of crap and I would have to prove everybody's. So no. But you can use them in lab all you want. That is a tool.
We use this piece of paper on the test.
What?
We use this piece of paper on the test.
Okay, everybody, eyes up here. The question has been twice now. Can we use this on the test? I'll tell you like my kids, you can keep asking me, the answer's still going to be no. Because you will still write other stuff on there.
But you'll write on the whiteboard or the formulas that we say. Right?
If you're a nice class, yes. If you're not, I'm going to say good luck to you.
Wow.
That's E effective. E effective equals 0.707 times E max. So I look at the max or the peak voltage, and I'm going to get the effective is 0.707 times that. The I effective is equal to, guess what? 0.707 times I max. Nice movie place too. That's what they got the name. E max. What if I know the E max? Let me see. If I want to know the multiply the max, if you know the max, multiply times 707, you get the effective. What if you know the effective and you want to go towards max? It's 1.7. I'm sorry, I'm just going to screw it up because I was thinking yes, you can divide. 1.414. 1.414 times E effective and I effective. No, I max is the same. I max equals 1.414 times I effective. Or we can divide. All right. For all practical applications, this is important. The value stated is RMS unless otherwise stated. For example, another important point. And this is the answer to one of the questions I ask you in the AC thing. I say, what are some of the limitations of voltmeters? Most instruments. That would be a VOM, voltometer, otherwise known as a multimeter, are measuring RMS, not peak or peak to peak. So you're either going to get peak to peak, or RMS. What does your meter read? RMS. What does the oscilloscope show me? Peak to peak. Those are two different things. So they're not going to agree with each other. So questions for you. Household voltage measures what?
110 or 120.
I know. Why does it say 110 or 120? Because it's somewhere in between, right?
It's because there's the error, just like with resistors, there's
Yeah.
an error.
Who's got a voltmeter with them? Seth, whip it out. Plug it in the wall. No, I'm serious.
Yeah, you can do it.
You can do that?
Yeah, it's a standard.
You're kidding, right?
No, you can do it.
Hey, this is from Amazon. Find out the mark for the day.
So we need to
Oh, the middle one.
Yeah.
Can we do it?
Was it
Okay. You got it?
Ow!
117.5. You can pull it out, sorry. I was just afraid. 117.5. So we got one. Let's round to, well, we'll just call it 120. There we go. So measure 120. 120 what? Volts.
Effective.
Not effective.
RMS.
RMS. Okay. What is then E max? What is the max?
169.
What is it really?
So how are we going to do that?
1.414 times 120.
120
Times
times 1.414. So we're going to go back to this one. I have the effective. I have the effective. So so I'm going to look at this one. E effective is what I'm after. I'm sorry, I have the effective. So
You need the E max.
I need the E max. I need this one here. There we go. Thank you. I need E max. So E max equals 1.414 times the effective. He just measured the effective. So effective was 120. So 120 times 414 equals
169.68.
169.68. Is that peak or peak to peak?
It's peak.
Okay. So gotta think about what we're doing here.
Wait, 169.68 volts.
Yep. That right here, volts, is our effective. Is it peak or is it peak to peak?
It's peak. Isn't that Emax?
What?
So that's our Emax.
That's our Emax.
Yeah.
Emax. But is it peak or peak to peak?
Peak.
It's gonna be peak. And the reason why is because you don't want to start doubling stuff. All right? Because remember, it's 0 to here is what we just measured. We just measured from 0 up, and we got 117. Then we figured out it's actually 169. Now, if I want to know peak to peak, what is peak to peak?
169.68 times 2.
2 times
So it's just got to multiply it times 2. So 169 times 2 is 339.36 volts. Volts peak to peak. So what is our real volt? What is our voltage coming out here? It's 339.36. Is that right? No, it's not right. It's peak to peak. I just doubled it, so can't do that. But our effective voltage is running about 707 times. So this is about our effective voltage is right along in here, right? So we have peak, peak to peak, and effective is somewhere around there, which is 0.707 times 1 peak. All right, we have enough time for one more question then. If a certain circuit has a peak voltage, so peak voltage of 56 volts, as indicated on an oscilloscope. So that's the O-scope voltage. What is the RMS? And let me see.
39.
And what is peak to peak?
59. RMS. And 12.
What'd you come up with?
39.59.
Everybody get 39.59 volts. The reason why is because it's 56. I just told you it's 56. Is that that's peak? Is that effective or max? That's max. So it's 56 times 0.707 equals 39.59. And peak to peak would be times 2, which is
112.
112? Oh yeah, a peak because it's of this. It's not this times 2. It's not 39 times 2. It's 56 times 2. Why? Because look at my graph right here. Effective is 0.707 times the peak. What is peak to peak? It's twice the peak, not twice the effective voltage. That's something completely different.
So when it's peak to peak, then you times it by 2, and then it's
No. Okay, so I kind of did this for a reason. RMS is out of order from this. There's peak voltage, which is 56. What is peak to peak? Peak voltage is 56. How much is peak to peak?
Twice.
It's twice that.
Double it.
But I asked them out of order. I said, what is peak? Then I said, oh, what is RMS? And I said, oh, what is peak to peak?
You know what your peak is.
These two things go together. Do it here. These two things go together. This one is a whole nother question. I asked them out of order. RMS is 0.707 times the peak. Peak to peak is 2 times this right here, the peak. Got it? So if I would have asked it different, I would have said, oh, what is, you might have got it. What?
How do you know?
Can you guys settle down?
How do you know what formula to use?
All right. So how do you know what formula to use? Well, you've got to know that effective is less than peak.
Yeah.
So if I have peak, do you think I want and I want effective? Should I multiply it by a number that's going to give me something higher or a number that's going to give me something lower?
Something low.
There you go. So you just got to ask yourself that. Hey, I've got effective and I want peak, then I better multiply it by something that's going to get me a higher number.
Okay.
All right. Now you can go. You guys are in such a hurry to stand there.